welcome in linear control systems and W341, and up to now we covered the steady state error in detail with examples, and in this lecture we will try 2-3 examples and the last topic related to the sensitivity. And first of all, uh, what will be the outline of this lecture? After reviewing the examples and the topic of sensitivity, uh, we have we are going to introduce the new important topic, which is the root locus. And root locus, in the point of view when we want to analyze the systems, in this aspects we discuss the root locus, and these concepts will be helpful to design the concepts. And root locus is more strong analysis as compared to the other analysis. And again, uh, now we are discussing the analysis part, and hopefully if we review our and develop the complete concepts of analysis, then it will be helpful to analyze and the to design the systems, and that error free systems and have the stability factors, and in frequency domain, also in time domain. So it is again related to the CLO2. So we have a second order servo and with unity feedback, and the open loop transfer function for this is given equal to 500 over s times s plus 15, and we want to analyze the steady state error for the input RAM input of 0.5 radian per second. So block diagram to represent the whole systems is like this one. It is a unity feedback and open loop transfer function which is given. And if the open loop transfer function is given, then we can find the error signal through this relation, which is already derived input over 1 plus the open loop transfer function, here h of s equal to 1. So steady state error from this definition is, uh, by applying the final value theorem, we can develop the definition of steady state error in this case. And after substituting the open loop transfer function, where this g of s is given in this one, and if we substitute here, then and after simplification we have in numerator terms r, and this s is belong to the definition of error signal and the steady state error, and this s is belong to the steady state error definition, and this r of s is related to the error signals. And this s and times in numerator term times the s plus 15 is related to the open loop transfer function, and the denominator of the steady state error is the simplification factor. If we substitute this 1 plus g in this, and the denominator terms becomes s k plus 15s plus 500. Okay, in this example, input is given is the 0.5 RAM function. So Laplace transform, because we are all discussion in the frequency domain, and we are reducing the results in time domain by applying the final value theorem. So in frequency domain we have input 0.5 over s square, it is related to the RAM input. And if we substitute this RAM input here, and this s square is cancelled out with this s, and s, both s is cancelled out with the s square, and after simplification we have a result is like this one: 0.5 times s plus 15 over s square plus 15s plus 500. And if we apply the limit s approaches to 0 due to the final value theorem, and this s in denominator term and in numerator terms are equal to 0, so finally we find the error is 0.15 radian per second. Okay. uh, so for different values uh, for different values of the input, we find through the simulink, this is the input in yellowish color, and this purple color representing the output, and it deviate heavily, especially I take it as a positive feedback, so it's heavily deviate. And if we simulate the same parameters we as we discussed in the example, then we find that both the inputs yellow color and the purple color approximate matching, and only small deviation, there is some fixed deviation. So this is the result related to the example. Okay, due to the demand of the students that try to different examples, so I am taking 2 or 3 examples to review the fundamental concepts, and these examples are now conventional, so we are taking something which is different. For example, in this case we have a unity feedback servo driven instrument, and open loop transfer function is 10 over s times s plus 12, and we have to find the steady state error for the input is 1 plus 4 t, which is different input as we usually discuss in the different lectures. So uh, in this case open loop transfer function is this one, and the error by definition of the error steady state error in terms of the error signals is given by this relation, and this s is related to the final value theorem. And if we substitute these values of open loop transfer function, then we have the steady state error in terms of input, and the definition related s, and this s times s plus 2 is the open loop transfer function denominator terms, and the steady state error denominator term of this is equal to s square plus 2s plus 10, and we have 1 plus 40 is the input. So we will take the Laplace transform, and have Laplace transform is 1 over s plus 4 over s square, and after simplification we have s plus 4 over s square, and by substituting the input value, this s square is cancelled out here. Last In the last slides we have s here and also s here. This s is cancelled out by the s square. So finally we have these terms, and after applying the initial value s approaches to 0, and we have steady state error is zero point 0.8. You can simulate it using the command and also by using the simulink. It's a simple. So in the next example we have to find the steady state error for unit input, and we will guess this input also, and this is the non-unity feedback. There are method to convert into a unity feedback, otherwise we can also find by using the forward transfer function. So if g1 is the of this transfer function of this for this block diagram, and h of s is the this g1 is the forward transfer function for the given systems, and h of s is the feedback transfer function, and the for whole forward transfer function is equal to this one. Directly we find the transfer function which is equal to this one, and if we substitute these values uh, and we find that g1 is equal to 10 times s plus 10, and divided by s times s plus 2, and similarly h of s is equal to s plus 3. After substituting and after simplification, we find that the forward transfer function for the given systems is equal to this one. So this is the forward transfer function which is given, and numerator terms is 10 times the s plus 10, and denominator terms is the second order, which is 10 11s square plus 132s plus 300. You can simplify maybe this value and find the steady state error for this one. First of all, we find that this system is type 0, and type 0 we can maximum find that the existing error is the step input. So test signal for this would be a step input, and the corresponding coefficient is the error constant is the position constant, and definition of the position constant is given by this one, and directly we apply the definition of this one, and we find that this is equal to this one. And if the position constant is given, then we can find the steady state error. It is equal to 1 over 1 plus kp, and we finally find that steady state error equal to 3 quarter. And next part is the find the steady state value of the actuating signal, and for the given systems actuating signals is lying by this one, and we already described that if this is the unity feedback, then difference between the input and the output is giving the error signals, and here is the actuating signal if it is the non-unity feedback. So how we find the steady state value, because we already decide that this type of systems uh, we can maximum apply the step input, and here we find the error signals, and the error signals is if we using a given data and the input value, and this type of is already covered in the start of the chapter in steady state errors. And this is the input, and g1 is the forward transfer function, and hf is the feedback transfer function. And if we use the given values, and we already decided for this type of systems we can use the step input, and the Laplace is equal to 1 over s, and if we apply these values we find that steady state value for the actuating signal is equal to 0, but we find that steady state error is equal to constant. So this is the difference between the actuating value and the steady state value. Hopefully this will be helpful to describe different type of system for especially for the non-unity feedback systems. So next example is to design the value of k for the input when there is 100 t u of t. So it is a ramp function, and and the allowed error is 0.01 in the steady state. So with the given transfer function, which is k over s times s plus 11. So from the transfer function, it is we can find that it is a type 1 systems, and for type 1 systems we required to find the steady state error, which is usually constant, is the RAM input. So for RAM input signal, this allowed error is 0.01, and the steady state error is the reciprocal of the uh, error constant. In this case is the velocity constant, but usually we take the unit RAM, but in this case it is a slope is 100. So we change this definition accordingly, and first of all we have to find the value of k. where k we can find the value of k. First of all, we have to type the values of this kv is equal to limit s approaches to 0, and s and g is the k over s plus 11 times s, and this s is cancelled out with this one, and is s is 0, then it is equal to k by 11, and substitute this value in the definition of steady state error, then we can find that this is according to the definition, and value of the velocity constant is this one, and it is equal to the allowed error, which is 0.01. So finally we find the value of k. So next example is to design the value of k for the input when there is 100 t u of t. So it is a ramp function, and and the allowed error is 0.01 in the steady state. So with the given transfer function, which is k over s times s plus 11, so from the transfer function, it is we can find that it is a type 1 systems, and for type 1 systems we required to find the steady state error, which is usually constant, is the ram input. So for ram input signal, this allowed error is 0.01, and the steady state error is the reciprocal of the uh, error constant. In this case is the velocity constant, but usually we take the unit ram, but in this case it is a slope is 100. So we change this definition accordingly, and first of all we have to find the value of k, where k we can find the value of k. First of all, we have to type the values of this kv is equal to limit s approaches to 0, and s and g is the k over s plus 11 times s, and this s is cancelled out with this one, and is s is 0, then it is equal to k by 11, and substitute this value in the definition of steady state error, then we can find that this is according to the definition, and value of the velocity constant is this one, and it is equal to the allowed error, which is 0.01. So finally we find the value of k. Okay, we will try to describe this definition of the sensitivity. Actually, every electrical or mechanical or electromechanical or any fluid systems, it it is usually it is sensitive with the some environmental or the linked parameters, and ideally we required the system parameter are lesser depends, but actually it is depends on the sensitivity. For example, if we are talking about the semiconductor devices based systems, then it is depends usually depends on the temperature, and first of all we try to apply those electrical or component or electronic component or electronic devices which are less sensitive to the temperature. Otherwise, if we want to, if there is a device which is dependent on the temperature, and it is directly uh, involved with the sensitivity, then we can find the sensitivity of those parameters, and uh, actually we required system which is uh, less sensitive to the any parameters linked to the systems. So formally we can define the sensitivity Actually, it's the ratio between the fractional change in the function. In our cases, we usually it is a transfer function, and to the ratio of the fractional change in the parameters, which are we are going to. This is the that parameter. So it is more appropriate way to define the sensitivity. So sensitivity S is dependent on the function f and the parameter, and where we apply the limit s approaches to 0 in S domain, and sensitivity is the ratio between the fractional change in the function, for example f, and to the ratio of the fractional change in parameter. So mathematically it is equal to the delta f by f, which is a fractional change in the function, or delta p by p. So delta p by p is the fractional change in the parameter, p representing the parameter, and delta p is the accordingly changes. And this definition, if we apply the limit s approaches to 0, then it is equal to the derivative. Actually, we are going to find the sensitivity of this function with respect to p by using the dependency and the change variation with respect to that parameter, and scaled by this factor, which is p by the total function. So this is the appropriate definition, and we formally use uh, to define the sensitivity. And for example, we have to calculate the sensitivity in this case, for example, we have a unity feedback closed loop systems, and where g1 s is the open loop transfer function, which is given is equal to k by s times s plus a, and it is unity feedback, so h of s equal to 1. We have to find the sensitivity which is changes due to the parameter of a, and ultimately we want to find the sensitivity, how to reduce it. So closed loop transfer function in this case is equal to this is the definition of the closed loop transfer function, and this is g1s is the open loop transfer function divided by the 1 plus open loop transfer function times the transfer function in the uh, closed loop transfer function, which is using in the feedback systems. So in this case it is equal to h s equal to 1, and if we substitute this open loop transfer function value, we find the closed loop transfer function, and this function is represented by capital T. It is equal to k by s square plus as plus k, and k may be some gain parameter, and a is the coefficient, and this is our parameter to want to describe and how this is the uh, affect the systems. So by using the definition of the sensitivity, we have the sensitivity of a function t, which is a closed loop transfer function and dependent on the parameter a, and it is scaled by the parameter times the transfer function, and we substitute here the closed loop transfer function, and we are taking the derivative of transfer function with respect to a parameter. And if we find these parameters and substitute into the relation, and we have the final relation is like this one. So this is the sensitivity we have find here, which is dependent on a, and here we can find data that from the final relation of this sensitivity, we can find that there is this parameter k in the reciprocal, and these things shows that if we increase the value of k, which is the gain or proportional controller, if we value of this k is increased, then sensitivity can be reduced, which is dependent by the parameter. And this is the very interesting factor, which will be this is in the next major topic, which is the root locus. How much we can change the value of k, and what effect on the this parameter depends on the stability. It is already covered in different aspects already in terms of stability, in terms of steady state error, but how this will affect the overall to the analysis part by using the values of k. So it will be the next part of our lecture. So now we are going to describe the next important part of the lecture, which is the root locus. So this new topic is very interesting, and so root means the path, and locus is the that curve and the behavior of the systems which is mathematically models, and how this effect will be studied. And this root locus is the important part of designing. So before going to the design part, we have to study the root locus in analysis part, and it will cover the all aspects which we already covered in terms of uh, stability and in the transient analysis, and usually uh, in the steady state errors. And root locus actually it is representing the graphical representation of a closed loop transfer function. Usually this is with the closed loop transfer function, and it will also study the stability and transient analysis, and graphically we can understand the behavior. So if we have a computer, then we can easily plot or draw the behavior of a open loop and closed loop transfer function. Even we can compare it. But if we don't have a computer, then how to find the behavior of the systems? And so this is the techniques which will be used to analyze. So finally, it is the qualitative discussion of the control system performance. So uh, already we covered is the usually is the quantitative discussion, so this is the qualitative discussion. So this is about the root locus. We formally discuss the definitions in brief in different aspects in the coming part of the lecture, even in the next lecture. But so starting from the some mathematically form of the root locus. So first of all, try to some review part later to the root locus. So for example, we have a system which is a closed loop system with negative feedback, and kg is representing the open loop transfer function, where k is the parameters which is very important in this case, which is the controller part. And here the complete this kgs representing the controller part, system and the actuator transfer function, the whole it is in a combined way. And h of s representing the transfer function of the feedback system through which we are measuring the feedback, so it is the transfer function of the feedback systems. So closed loop transfer function, as we this is already in even in this lecture, the closed loop transfer function is equal to kg over 1 plus kgh. So this is the closed loop transfer function, where G representing the forward path transfer function, and H of S is the feedback path transfer function. Okay, this is the closed loop transfer function, and if we represent of these transfer function G and H in terms of numerator and denominator terms of the transfer function. For example, n sub g representing the numerator terms of the transfer function, which is representing the zeros of the open loop transfer function. So this term representing the zeros of the transfer function in an open loop, and this term representing the poles of the uh, open loop transfer function, and this is the denominator terms of the open transfer function. And similarly, we have this n sub h is the numerator terms of the feedback transfer function, and this represent the poles zeros of the uh, feedback transfer function, and this denominator terms represent the poles of the closed loop feedback transfer function. So if we substitute these terms in the closed loop transfer function of the system, then we have uh, the closed loop transfer function in terms of these parameters like this one. And if we simplify this relation, then we have terms like this one. So first of all, we review this k is important, and this k is the most important thing in the root locus part. And this, so overall, this is the product of, so numerator term is the zeros of the g transfer function, and d is the denominator terms is the poles of the h. So it is the product of the zeros of the g and the poles of the h. And denominator terms is the, again it is a combination of different terms. For example, it is depends on the poles of the g and poles, product of the poles of the h, plus k times the zeros of the g and zeros of the h. And the whole thing is the closed loop poles, which is important, and it is dependent on the k. If the value of k is fixed, then there is a fixed number of poles, and if we change the values, then these location of the poles is changed. This discussion is already covered in the transit analysis, in the stability factors, also in the steady state errors. So this is most important thing here. And next, we will try to cover the some numerical examples to understand these concepts. Let's try by using some numerical examples to understand the concept of related to locus parameters in a closed loop transfer function. For example, g of s is systems which have zero. It is a forward transfer function at 0 at -1 and pole at 0 and -2. And similarly, feedback transfer function have a 1 0 at -3 and 1 pole at -4. And if we combine the effect of the closed loop transfer functions and this part of the transfer function is a open loop transfer function, the whole systems, and numerically we find that in a open loop transfer function we find there are two zeros at -1 and -3, and poles at lies at 0, -2 and -4. So this is the open loop transfer function. So description is simple, but if we discuss the closed loop transfer function, then by using the numerical values of these parameters, then we find the closed loop transfer function. And from the closed loop transfer function we find that there are zeros. We can clearly find the zeros in a closed loop transfer function. One zero is at -0, and other is at -2, and third one is at -4. But what about the closed loop poles? We cannot describe the poles of the transfer function unless we define the final value of k. So it is totally dependent on the k. So this is the important factor which we describe in the root locus. So root locus, we describe that the poles of the closed loop transfer function, it changes with the values of k when we vary from 0 to infinite. So this is the concept which we will dive, and this is in detail in the root locus analysis part. The next examples, we find that there is a 1 0 and there are two poles in the forward transfer function, and the feedback transfer function had 1 0 and one pole lies at -8 and -2. So if we find the closed loop transfer function, then the part of the part of the open loop transfer function which is dependent on the k, how these poles are varies, let's see through the simulation. If we simulate these the closed loop transfer function with the different values of k, these values are changing from k0 to k20. So if we change the values from k0 to zero point 0.5, so these poles are lying here, and up to, if we change the values at zero point 0.5, then these poles are lying in a complex plane, and further we increase the values of k, and these location of the poles are changes accordingly. So one pole is path of one pole, it changes in this way, and symmetrically the other poles positions are changes with the variation of k by increasing the values of the k. So this is the concept related to the root locus, and next we will describe in detail, and the summary of the lecture is, in this lecture we review the concepts of steady state error by doing some fundamental examples, and then defines and the sensitivity, and understand this sensitivity by using the single examples, and then we describe the root locus, and this root locus is variation which is in the closed loop transfer function with the variation of the proportional constants which is changing from 0 to infinite, and we will continue this discussion in the next lectures. Okay, thank you so much.